This is element 31, a metal that melts in the palm of your hand, but its true power lies at the atomic scale, powering the core of our digital world.
So I want you to just try to imagine an impossible scenario for a second here.
Okay, I'm with you.
Imagine you're holding this solid, cold piece of metal right in the palm of your hand.
Right, like just a standard piece of metal.
Exactly, yeah. It feels heavy, it's completely rigid, looks exactly like, just some shiny metal you pick up at a hardware store.
Mm-hmm.
But as you sit there, just holding it, this really bizarre thing starts to happen.
Let me guess, it doesn't stay solid.
Right. Without any blowtorches, without like industrial furnaces or anything, that hard piece of metal just slowly begins to soften.
Wow.
Yeah. Within minutes, it literally collapses into this heavy, silvery liquid puddle.
Mm-hmm.
And it's melting purely from the natural warmth of your own skin.
Which is crazy to even picture.
I mean, if you were watching this happen, your first instinct wouldn't be, oh, that's science. Your first instinct would be that someone is doing a magic trick.
Oh, it absolutely feels like an illusion. And well, that's because it completely violates our baseline expectations of how the physical world is supposed to operate, Totally. Metals are supposed to be tough.
Right. When we think of melting metal, our minds immediately go to extreme environments. We think of sparks flying, massive industrial crucibles, people in protective thermal gear.
Yeah, you don't think of bare hands.
Exactly. I mean, to melt iron, you have to push the temperature well past 1,500 degrees Celsius.
Wow, okay.
Even aluminum, which we consider relatively lightweight, that requires over 660 degrees Celsius just to turn into a liquid. So we are wired with this binary understanding. Metals are hard, and turning them to liquid takes a monumental amount of thermal energy.
Right, because they're the things we build skyscrapers and bridges out of. But the main character of our deep dive today takes all of those established rules and just kind of throws them out the window.
It really does.
Today we are unpacking the story of element 31 on the periodic table, gallium.
Yes, the shapeshifter. Yeah, this is a metal with a melting point of roughly 29.8 degrees Celsius. So if you're sitting in a normal, slightly cool room, it's a solid block. But your standard body temperature is more than enough to turn it into a puddle.
And that contrast right there, that's the central mystery we are unraveling in this deep dive.
Yeah.
How did a strange, shape-shifting metal that literally melts in your bare hands become one of the most critical, foundational elements of modern technology?
Because it really is everywhere now, right?
Oh, absolutely. If you're listening to us on a smartphone right now or, working on a laptop, you are relying on this very metal.
Okay, we definitely need to unpack this. Because on one hand, it sounds like a parlor trick, but on the other, it's like the invisible backbone of the digital age.
Yeah.
But before we figure out how a melting metal powers our world, we really need to understand what exactly this bizarre material is. Like, where does this even come from?
Well, chemically speaking, gallium carries the symbol Ga, and it sits right there at atomic number 31 on the periodic table. And if you were to look at it in a cool room, you really wouldn't suspect a thing. It's shiny, it has this sort of silvery blue tint to it, and it actually fractures like glass if you try to bend it when it's solid.
Oh, weird.
Yeah, but despite how important it is, it's relatively rare in the Earth's crust.
Wait, when you say rare, do you mean it's like gold or platinum? Are there people out there panning for gallium in rivers?
No, not quite like that. It's rare in a different way. You don't really find massive, pure veins of gallium in the ground waiting to be mined.
Oh, okay.
It doesn't really exist by itself in nature. Instead, it's extracted as a byproduct.
A byproduct of what?
Well, when industrial mining operations process the ores of other metals, specifically aluminum ores like bauxite or zinc ores like sphalerite, they find these little trace amounts of gallium just mixed in.
That is so weird. It's basically a stowaway.
That's a great way to put it, actually.
It's just hitching a ride inside these giant rocks of aluminum and zinc, completely hidden till we break them open. But hold on, I'm thinking about this logically here.
Sure.
If it looks like a normal metal and it's literally hiding inside aluminum and zinc rocks, why doesn't it behave like them?
Ah, that's the big question.
Right. Like, why is it so structurally weak at room temperature that my hand can melt it, but the aluminum it hides inside needs a literal furnace?
That is the perfect question. And the answer really comes down to a kind of atomic identity crisis.
Identity crisis, what do you mean?
So most metals require high temperatures to melt because their atoms are locked together in this highly structured, tightly packed 3D grid We call it a crystal lattice.
Okay, like a really strong scaffold.
Exactly. The bonds between those metal atoms, the metallic bonds, are incredibly strong. They share electrons freely, pulling the whole structure tightly together.
Right.
But gallium doesn't do that. Instead of this massive grid, gallium atoms tend to pair up into molecules. Two atoms bonded together, which we call dimers.
Wait, so instead of a massive unified grid holding on for dear life, they just pair up into couples?
Exactly. Inside solid gallium, you have these distinct pairs of atoms. The bond between the two atoms in a pair is really strong, but the forces holding one pair to the next pair are incredibly weak.
Oh, I see.
Yeah, it's almost acting more like a molecular solid, sort of like iodine or dry ice rather than a true metal. Because the forces between these pairs are so weak, it takes barely any energy at all to overcome them.
Okay. So when I apply just a tiny bit of heat from my hand, I'm not having to rip apart some massive reinforced steel-like grid.
Nope.
I just have to gently nudge these little pairs apart so they start sliding past one another.
Precisely. You're just giving them enough thermal kinetic energy to stop sitting still and start flowing.
That makes so much sense.
But you know, what's truly mind-blowing about gallium isn't just its weak atomic structure. The strangest part of its history is that scientists knew all about it long before a single human being had ever actually seen it.
Yes, the ultimate scientific detective story. I was actually reading through the sources about this, and they talk about this French chemist, right? Paul-Émile Lecoq de Boisbaudran. He officially discovered and isolated gallium in 1875.
Right.
And he actually named it Gallia, which is the Latin name for France. But the real genius of this story happened decades before the French even found it.
That's right. To really appreciate gallium, we have to look at the Russian chemist Dmitri Mendeleev, the man who basically created the modern periodic table.
Right, the guy who put the puzzle together.
Exactly. When Mendeleev was arranging all the known elements based on their atomic weights and their chemical properties, he noticed distinct patterns. But he also noticed gaps. There were blank spots where the math and the chemical logic dictated an element simply had to exist, even though nobody had found one yet.
And he didn't just shrug and leave it blank, right? He hyper-focused on the gap right below aluminum.
He did. He called this missing element Eka aluminum. The prefix Eka comes from Sanskrit, meaning one. So he was essentially saying the one space below aluminum.
Oh, okay, that's clever.
And he didn't just name it, he predicted its exact properties based entirely on the trends of the surrounding elements. Wow.
He calculated its approximate atomic mass. He predicted its density. He even calculated how it would react with oxygen. All of this on paper for a metal that, as far as the scientific community knew, was just a ghost.
That is so incredibly bold. I love this. It's exactly like hosting a massive dinner party, right?
Okay, how so?
Well, you leave one chair empty at the table, and you tell all your other guests, oh, the person who will sit here is going to be exactly 5'9" tall. They'll be wearing a blue jacket, and their favorite dessert is strawberry ice cream.
Yes.
You're telling them this, and the person hasn't even RSVP'd. You haven't even met them.
It's a brilliant analogy, really, because the guests would think you were crazy until that exact person walks through the door.
Right.
And that is exactly what happened in 1875. When Lecoq de Boisbaudran finally isolated gallium and measured its physical properties, the scientific world was absolutely stunned.
Because the numbers match?
Almost perfectly. The atomic weight, the density, the chemical behaviors, they almost perfectly matched Mendeleev's predictions from years prior. Mendeleev basically proved the periodic table wasn't just like a filing cabinet. It was a predictive engine. It was a mathematical map of the universe.
Exactly. It established the predictive power of the periodic table, making it one of the greatest scientific breakthroughs of the 19th century. He saw the underlying mechanics of nature.
Okay, so Mendeleev nailed the math on paper. But dealing with physical gallium in the real world is a totally different experience than reading about it in a textbook.
Oh, absolutely.
Let's go back to that melting point, 29.8 degrees Celsius. If I'm holding this in my hand, what is actually happening? Because it doesn't just instantly vanish the second my skin touches it, right?
No, it's not an instant vanishing act. The phase change from a metallic solid to a flowing liquid is a process. It's governed heavily by thermodynamics. It all depends on heat transfer.
Okay, so how does my body heat factor in?
Well, your internal core body temperature is roughly 37 degrees Celsius. However, your exterior skin temperature usually hovers around 32 to 34 degrees Celsius.
Okay, which is just a few degrees above that 29.8-degree threshold.
Yeah.
So it's not like dropping an ice cube onto a sizzling 400-degree frying pan.
Exactly. It's a very shallow temperature gradient. So the melting process is much more of a slow, gradual surrender to your body heat. And there are several variables at play here.
Like what?
First, ambient temperature. If you're sitting in a freezing cold room, the room is actively cooling the metal while your hand is trying to warm it, which really slows the process down.
Oh, that makes total sense. What about, like, the size of the metal piece?
Volume is a huge factor.
Yeah.
Heat takes time to conduct through a material. If you have a massive chunk of gallium, the surface touching your skin might start to soften, but the center remains solid because the thermal energy just hasn't penetrated that deep yet.
Right, right.
And finally, there's surface area contact. If you hold it flat on an open palm, it melts slowly. But if you close your fist around it, tightly gripping it, you are transferring heat from all sides simultaneously.
Right.
Yeah, the weak intermolecular bonds we talked about earlier begin to break apart, and you'll slowly feel this heavy, dense, silvery liquid pooling right there in the creases of your hand.
That is just such a visceral, bizarre thing to experience.
Yeah.
But wait, if those intermolecular bonds are so weak that my body heat can literally shatter them, what exactly happens when you take that heat away?
You mean when it cools down?
Yeah, when it cools down and tries to rebuild those bonds.
Yeah.
Because I was reading the sources, and apparently it breaks one of the most fundamental rules of chemistry.
Oh, absolutely does. The anomaly of how it freezes is just as strange as how it melts.
Seriously.
Yeah. There is a general rule in physics and chemistry. As a substance cools down and transitions from a high-energy liquid state to a lower-energy solid state, its atoms lose kinetic energy.
Right, they slow down.
Exactly. They stop moving around so much and they pack tightly together. The material contracts, it shrinks.
Okay.
But gallium just refuses to follow that rule. When gallium freezes, it actually expands.
It expands. Wait, like water?
Exactly like water. Water is one of the very few exceptions we experience daily.
Right.
When water turns into ice, its hydrogen bonds force the molecules into a rigid, open, hexagonal structure, which is why ice takes up more space than liquid water and floats.
Okay, I remember that from science class.
Well, gallium pulls a very similar trick. As it solidifies those molecular pairs we talked about, the dimers, they arrange themselves into a highly complex open lattice structure.
An open lattice, what does that mean practically?
It means that to accommodate the specific angles and lengths of its chemical bonds, the solid structure actually contains more empty space between the atoms than the chaotic liquid state did.
Wait, really?
Yeah. Because of the structural shift, gallium's volume increases by about 3.1% when it freezes.
Okay, if I'm picturing a chemistry lab right now, this sounds like a disaster waiting to happen.
Oh, you have no idea.
Because I've definitely made the mistake of leaving a glass bottle full of water in the freezer, and I come back to find it completely shattered because the ice just needed more room.
Yep.
If I have a glass jar full of liquid gallium in a lab, and the air conditioning kicks on overnight, is it going to explode?
It absolutely will shatter its container. If you fill a rigid glass or metal jar to the brim with liquid gallium, seal it tightly, and let the temperature drop below 29.8 degrees, the metal will begin to crystallize.
Oh boy.
And the mechanical force of a crystallizing metal expanding by 3% is immense. It will easily rupture glass and tear apart metal seams.
That's wild.
Because of this, standard laboratory protocol dictates that gallium must always be stored in flexible containers like plastic or in jars that are only partially filled, to leave room for that expansion.
Wow. Okay, breaking its own storage jar is definitely annoying for a scientist. But what this metal does when it comes into contact with other metals is borderline terrifying.
Oh, you're talking about the aluminum issue.
Yes. I want to talk about what it does to aluminum.
This is a phenomenon that is incredibly famous in materials science. When liquid gallium comes into physical contact with an aluminum surface, it initiates a severely destructive process. We call it liquid metal embrittlement, or, more simply, amalgamation.
Okay, you need to break this down for me. Because if I picture a block of structural aluminum, like the stuff we make ladders and airplane wings out of, it just looks like one solid, continuous, impenetrable block of metal.
Right.
How does a tiny liquid puddle destroy that?
Well, that's the illusion of the macroscopic world, right? To the naked eye, it looks continuous. But if you look at aluminum under a really powerful microscope, it's not one single block.
What is it?
It's actually made up of millions of microscopic individual crystals, which we call grains. Think of it like a tightly packed 3D jigsaw puzzle.
Okay, I'm with you. So it's millions of tiny puzzle pieces tightly bonded together.
Right. And the spaces where those puzzle pieces meet are called grain boundaries. Now, normally, aluminum forms a thin layer of oxide on its surface that protects it from the elements. But if you scratch that oxide layer and put liquid gallium on it, the gallium does something incredibly insidious.
How does it do?
It chemically prefers to exist in those grain boundaries. So the liquid gallium atoms actively seep into the microscopic cracks between the aluminum puzzle pieces.
Wait, it just invades the structural gaps?
Exactly. It penetrates deep into the aluminum structure, and as it coats those boundaries, it severely weakens the intergranular bonds, basically the glue holding the puzzle pieces together.
Oh, wow.
Within a matter of hours, a thick, incredibly strong bracket of structural aluminum becomes so brittle that you can literally tear it apart with your bare hands.
Are you serious?
Yeah, it behaves like wet cardboard. Its mechanical strength drops to near zero.
That is genuinely shocking. A metal that can't even withstand the heat of my palm acts like a microscopic wrecking ball to one of our toughest building materials.
It really does.
Which raises a major question about safety. If you're handling this in a lab, I assume you have to be incredibly careful.
You do, but it requires a specific kind of care. From a materials standpoint, it is considered highly hazardous. You must keep it far away from aluminum tools, structural supports, and especially airplanes.
Oh, I bet.
In fact, there are strict restrictions on transporting gallium by air for exactly this reason. If it spills, it could literally eat right through the floor of the fuselage.
That is terrifying.
And you certainly don't want to wash it down a sink, because if it freezes and expands or interacts with metal pipes, it will destroy your plumbing.
Okay, but what about human safety? Is it toxic to us, like mercury or lead? Because it behaves a little bit like mercury.
That's the surprising part. Despite being structurally lethal to aluminum, gallium is not considered highly toxic to humans.
Really?
Yeah, you can handle it with your bare hands. Now, standard lab safety always applies, right?
Right.
You shouldn't casually play with it, you definitely shouldn't ingest it, and you must keep it away from your face and eyes.
That makes sense.
And when you melt it in your hand, it does leave a dark, grayish stain on your skin because microscopic amounts of the metal rub off into your pores. But compared to heavy metals like mercury, it is incredibly benign to biology.
All right, so let me just take a step back and look at what we've learned so far. We have element 31.
Yep.
It melts at a weirdly low temperature because its atoms prefer to hold hands in pairs rather than form a strong grid.
Exactly.
When it freezes, it expands and breaks its own jars. And if it touches aluminum, it sneaks between the microscopic puzzle pieces and completely destroys the structural integrity.
That's a good summary.
Honestly, this sounds like a chaotic anomaly that we should just lock away in a hazard cabinet. But from what I read in the sources, we didn't lock it away. We put it inside almost all of our most advanced, expensive technology.
And this is where the story shifts from a quirky science experiment to the literal foundation of the 21st century. The true value of gallium has nothing to do with it melting in your hand. Its superpower lies in its ability to form advanced alloys and, most importantly, its role in creating next-generation semiconductors.
Semiconductors?
Yes. Modern digital infrastructure, as we know it today, would basically stall without gallium.
Hold on. You're telling me the same weird, chaotic metal that ruins aluminum is the secret ingredient allowing my high-speed electronics to function? How?
Well, by itself, pure gallium isn't widely used in tech. The magic happens when you bond it with other specific elements.
Like what?
There are two absolute giants in the tech industry today: gallium arsenide, or GAs, and gallium nitride, GaN. When you combine gallium with arsenic or nitrogen, you create semiconductor materials that can do things traditional silicon could only dream of.
But wait, silicon is the undisputed king of the tech world, right? I mean, we literally named Silicon Valley after it. Why do we even need gallium?
Silicon is fantastic, and it is cheap, but it has severe limitations when you push it to its absolute limits. In physics, we talk about something called electron mobility. Basically, how fast and easily can an electron move through the atomic lattice of a material? In silicon, when you try to push data at super high frequencies, the electrons face resistance.
Right.
They bump around, they lose energy, and that lost energy turns into heat.
Which is why my laptop sounds like a jet engine when I'm running too many programs. It's just silicon getting hot.
Exactly. But in gallium arsenide, the crystal structure is different. The electrons can glide through the material with far less resistance. They move much faster.
Oh, wow.
Because of this high electron mobility, gallium arsenide is the go-to material for things that require extreme speed and high frequencies, like 5G smartphone networks, aerospace communications, and satellite uplinks.
So it's basically built for speed.
Exactly. Silicon just isn't fast enough to handle those ultra-high radio frequencies efficiently, but gallium arsenide handles it beautifully.
Okay, that covers the high-speed data.
Yeah.
But what about gallium nitride? Because I've been seeing GaN printed on all those fancy new super-fast wall chargers for phones and laptops.
Yeah. Yes, gallium nitride is completely revolutionizing power electronics. GaN can handle massive electrical fields and high voltages in a much smaller physical space than silicon.
Really? Just by switching the material?
Yep. Because it's so efficient and doesn't waste energy as heat, engineers can pack the components much closer together. That's why your new GaN charger is half the size of your old charger, but can charge your laptop twice as fast without melting the plastic casing.
That is wild.
It's fundamentally superior at managing power.
So gallium is basically the VIP pass for electrons.
Mm-hmm.
But I also read there's one more massive industry that gallium completely dominates, and it has to do with screens and lights.
Yes. This is perhaps its most visible contribution to your daily life. Gallium-based semiconductors have a very special quantum mechanical property called a direct band gap.
Okay, a direct band gap. You're going to have to explain that to me because I'm just imagining a literal gap that electrons have to jump across.
Well, that is actually a great way to picture it. In semiconductors, electrons have to jump across an energy gap to conduct electricity. When they jump back down to a lower energy state, they release the extra energy they were carrying.
Okay, makes sense.
In silicon, which has an indirect band gap, that energy jump is messy. The energy is released mostly as physical vibrations in the atomic lattice, which we feel as heat.
So silicon gets sweaty and hot again.
Exactly. But gallium arsenide and gallium nitride have a direct band gap. When their electrons make that jump and release energy, it's a perfectly clean transition. Instead of releasing heat, they release the energy directly as a photon, a particle of light.
Wait, so when electricity passes through gallium, it just naturally glows?
Precisely. It converts electrical current directly into light with incredible efficiency. This is the underlying technology of almost all modern light-emitting diodes, or LEDs.
No way.
Yes. Without gallium, we wouldn't have the brilliant red, green, and especially the blue LEDs that make up the pixels in your smartphone screen, your flat-screen TV, or the energy-efficient bulbs lighting your home.
That is incredible.
It's also the technology behind the lasers that read Blu-ray discs and transmit data through fiber optic cables across the ocean.
That is just, it's almost poetic, you know. The exact same metal that couldn't even handle the heat of my closed fist without falling apart is the exact reason I can scroll through a high-definition screen in the dark or connect to a 5G network from across the city.
It perfectly illustrates how complex the elements really are. A single element can play completely contradictory roles depending on the atomic context you put it in.
If you really step back and look at the whole journey of element 31, it's wild. We started with a ghost, a blank spot on a 19th century chart that a Russian chemist calculated using pure math and intuition.
Right.
Then it became a physical reality, a quirky silvery puddle that plays tricks on us at room temperature, shatters glass when it freezes, and tears apart structural aluminum like wet paper. And yet, scientists took that chaotic behavior, combined it with arsenic and nitrogen, and turned it into the invisible, high-speed, late-emitting powerhouse that essentially runs our 21st century digital lives. It is a wildly impressive resume.
It really is. But, you know, if we connect this all back to the very beginning, there is a profound, almost philosophical irony hidden in the sources about how this element was discovered.
An irony? What do you mean?
Think back to Mendeleev. When he predicted gallium's existence, he did so by looking at aluminum.
Right.
He called the missing element Eka aluminum, meaning like aluminum. He grouped them together in the same family on the periodic table because the math suggested their properties would be highly similar. He assumed a natural harmony between them.
Right, because they are stacked right on top of each other in the same column. They are elemental siblings.
Exactly. But as we just explored, when those two siblings, gallium and aluminum, actually meet in the physical, real world, there is no harmony at all. Gallium violently invades aluminum's grain boundaries and completely destroys its structural integrity at a microscopic level.
Oh, wow. I didn't even put that together.
It begs a really fascinating question. What other seemingly harmonious relationships, perfectly organized on the periodic table, are hiding destructive, chaotic secrets once they actually interact in the real world.
Man.
A model on paper can be mathematically perfect, but real-world chemistry always has the final say.
Wow. That is an incredibly wild thought to leave on. A mathematical prediction that was completely flawless on paper, yet in physical reality, the element aggressively destroys the very template it was based on.
Yep.
It's a reminder that science is never just a static list of facts. It is dynamic, it is messy, and it is endlessly surprising.
I am definitely going to be looking at the periodic table a little differently after this.
I think we all will.
Well, if you enjoyed this deep dive, I highly encourage you to look deeper into the stories of the elements. There are 118 of them, and every single one is an entire universe of weird behaviors and incredible applications just waiting to be unpacked. Keep asking questions, keep looking past the obvious, and we'll catch you on the next deep dive into the fascinating world around us.